What is 2's complement? How computers represent negative numbers. Computers naturally store patterns of bits. For unsigned integers, the idea is simple. With 8 bits, values can range from 0 to 255. But computers also need negative numbers, such as -1, -5, and -100. Modern computers normally solve this problem with 2's complement. It is one of the most important ideas in computer arithmetic because it lets positive and negative integers use the same basic binary addition hardware. In this lesson, we will see how 2's complement works, why it is useful, how signed and unsigned values can use the same bits, and what happens during addition, subtraction, overflow, and sign extension. Chapter 1. The problem: binary naturally represents positive numbers. Suppose we have 4 bits. There are 16 possible bit patterns, from 0000 through 1111. If we interpret them as unsigned integers, they represent 0 through 15. In general, n bits provide 2 to the power of n possible values. But ordinary unsigned binary gives us no negative numbers. If a computer calculates 5 minus 8, the result should be -3. So we need a rule that uses some binary patterns to represent negative values. Chapter 2. Why not just use one sign bit? A simple idea is to use the leftmost bit as a sign. 0 could mean positive, and 1 could mean negative. Then, for example, positive 5 could be 0000101, while negative 5 could be 100000101. This is called sign and magnitude. It looks simple, but it creates problems. The biggest example is 0. We would have both positive 0 and negative 0. Arithmetic hardware also becomes more complicated because positive and negative values need different treatment. 2's complement avoids these problems. Chapter 3. The basic idea of 2's complement. In 2's complement, positive numbers look exactly like ordinary binary. For example, in 8 bits, positive 1 is 00000001, and positive 5 is 00000101. Negative numbers use patterns whose most significant bit is 1. For example, 11111111 represents -1, and 11111011 represents -5. But 2's complement is not simply sign and magnitude. The whole bit pattern participates in the value. Chapter 4. How to create a negative number. To convert a positive binary number into its negative 2's complement form, use 2 steps. First, invert every bit. Second, add 1. Let us convert positive 5 into negative 5 using 8 bits. Positive 5 is 00000101. Invert every bit, 11111010. Then add 1, 11111011. So, in 8-bit 2's complement, 11111011 equals -5. The rule is simple: invert, then add 1. Chapter 5. Another example, representing -1. Start with positive 1, 00000001. Invert all bits, 11111110. Add 1, 11111111. Therefore, 8 binary ones represent -1 inside 8-bit 2's complement. The same pattern is also hexadecimal FF. As an unsigned 8-bit value, it means 255. As a signed 8-bit value, it means -1. The bits are identical. Only the interpretation changes. Chapter 6. The same bits can mean 255 or -1. Consider 8 binary ones again. The hardware stores only those 8 bits. If software treats them as unsigned, the value is 255. If software treats them as signed 2's complement, the value is -1. Memory itself does not store a label saying positive, negative, signed, or unsigned. A data type, instruction, or program tells the processor how to interpret the bits. This idea is fundamental. The same bit pattern can have different meanings in different contexts. Chapter 7. Why does 2's complement work? An 8-bit system has 256 possible patterns. Binary arithmetic naturally wraps around after 256. For example, if we add 1 to 8 binary ones and keep only 8 bits, the result becomes 8 zeros. The 9th carry bit is discarded. 2's complement uses this wraparound behavior. The pattern 1111111 can be viewed as one step below 0, so it represents -1. The next pattern down represents -2, and so on. This is why normal binary addition still works with negative values. Chapter 8. A useful way to think about negative values. There is another useful rule. For an n-bit 2's complement number, if the value is negative, you can treat the bit pattern as unsigned first, then subtract 2 to the power of n. For 8 bits, subtract 256. For example, 8 binary ones have unsigned value 255. 255 minus 256 equals -1. The pattern 11111011 has unsigned value 251. 251 minus 256 equals -5. This gives us another direct way to interpret negative patterns. Chapter 9. Why an 8-bit signed integer ranges from -128 to 127. 8 bits provide 256 possible patterns. As unsigned values, they represent 0 through 255. In signed 2's complement, the patterns beginning with 0 represent 0 through positive 127. The patterns beginning with 1 represent -128 through -1. So the complete signed range is -128 to positive 127. In general, an n-bit 2's complement integer ranges from -2 to the power of n-1 through positive 2 to the power of n-1 -1. Chapter 10. Why is there one more negative number? The signed range is not perfectly symmetrical. There are 128 negative values, 127 positive values, and 1 0. Why? Because 2's complement has only one representation of 0. There is no separate negative 0. That frees one extra bit pattern for a negative value. So in 8 bits, 100000000 represents -128. But positive 128 cannot be represented, because 0111111 or 127 is already the largest positive value. Chapter 11. How to read a negative 2's complement number. Suppose we see 11110110. We know it is an 8-bit signed value. Because the most significant bit is 1, the number is negative. To find its magnitude, reverse the 2's complement process. Invert every bit 00001001. Then add 1 00001010. That is decimal 10. Therefore, 11110110 represents -10. Chapter 12. A faster method. We can read the same value another way. Treat 11110110 as unsigned first. Its unsigned value is 246. Because this is an 8-bit signed value, subtract 256. 246 minus 256 equals -10. So the pattern represents -10. Both methods give the same answer. Use whichever method is easier for the situation. Chapter 13. 2's complement makes addition easy. The major advantage of 2's complement is that the same binary adder can work with positive and negative values. Consider 5 plus -3. 5 is 00000101. -3 is 11111101. Add them normally. The low 8 bits of the result are 00000010. That is 2. The extra carry beyond the 8th bit is discarded. So ordinary binary addition gives the correct signed result, 5 plus -3 equals 2. The adder does not need a completely different procedure for negative numbers. Chapter 14. Subtraction becomes addition. 2's complement also makes subtraction elegant. Instead of building completely separate arithmetic for a -b, the processor can calculate a plus -b. Negative b is created with 2's complement. For example, 7 minus 3 becomes 7 plus -3. 7 is 00000111. -3 is 11111101. Add them and discard the extra carry. The result is 00000100. That is 4. So subtraction can reuse much of the same addition hardware. Chapter 15. positive plus negative. Now consider 3 plus minus 5. Positive 3 is 0,000,000,011. Negative 5 is 111111011. Add them normally. The result is 111111110. In sign 8-bit 2's complement, that pattern represents minus 2. So, 3 plus minus 5 equals minus 2. Again, ordinary binary addition produces the correct signed result. Chapter 16. The most significant bit. In 2's complement, the leftmost bit is the most significant bit, or MSB. For an 8-bit signed integer, a pattern beginning with 0 represents a non-negative number. A pattern beginning with 1 represents a negative number. Because of this, the MSB is often called the sign bit. But remember, 2's complement does not store a separate sign in magnitude. The entire bit pattern represents the number. The leftmost bit tells us the sign, but all bits still participate in the value. Chapter 17. The leftmost bit has a negative weight. There is a mathematical way to read 2's complement directly. For an 8-bit signed value, the bit weights are minus 128, 64, 32, 16, 8, 4, 2, and 1. The leftmost bit therefore has weight minus 128, not positive 128. For the pattern 11111011, add the active weights, minus 128, plus 64, plus 32, plus 16, plus 8, plus 2, plus 1. The result is minus 5. This method lets us evaluate a negative 2's complement value directly. Chapter 18. What is signed overflow? A fixed-width integer cannot represent unlimited values. An 8-bit signed integer only covers minus 128 through positive 127. Now calculate 127 plus 1. 127 is 011111111. Add 1, and the 8-bit result becomes 100000000. But that pattern means minus 128, not positive 128. The true mathematical answer is outside the available signed range. This is called sign overflow. Chapter 19. Another overflow example. Consider 100 plus 50. Both values fit inside an 8-bit signed integer. But their mathematical sum is 150. That value is larger than the maximum signed 8-bit value of 127. So an 8-bit signed result cannot represent the correct answer. Processors often provide an overflow flag so software can detect this condition. Overflow is not saying the addition hardware failed. It means the mathematical result does not fit inside the chosen fixed-width signed format. Chapter 20. Carry and overflow are not the same thing. Carry and signed overflow are related, but they are not the same. A carry out of the most significant bit is especially useful for unsigned arithmetic. Signed overflow asks a different question: does the signed mathematical result fit inside the allowed signed range? For example, 127 plus 1 causes signed overflow. Looking only at the carry bit is not enough to describe what happened. This distinction becomes important when studying CPU status flags and arithmetic instructions. Chapter 21. Sign extension. Suppose we have the 8-bit signed value for minus 5, 11111011. Now we want to store the same value in 16 bits. We cannot simply add zeros on the left, because that would turn the value into a positive number. Instead, we use sign extension. Copy the sign bit into the new high-order positions. The 16-bit value becomes 11111111, 11111011. It still represents minus 5. Positive values are extended with zeros. Negative values are extended with ones. Chapter 22. Zero extension versus sign extension. Consider 8 binary ones. As an unsigned 8-bit value, they represent 255. To widen that unsigned value to 16 bits, use zero extension, 8 zeros followed by 8 ones. The value remains 255. But as a signed 8-bit value, the same 8 ones represent minus 1. To widen minus 1, use sign extension, 16 ones. The value remains minus 1. So even extension rules depend on whether the original value is signed or unsigned. Chapter 23. signed and unsigned in C. Programming languages expose this distinction directly. In C, for example, int 8t is a signed 8-bit integer, while uint 8t is unsigned. A signed 8-bit integer ranges from -128 to +127. An unsigned 8-bit integer ranges from 0 to 255. If the stored bits are 8 ones, uint 8t interprets them as 255. Int 8t interprets the same bits as -1. This is a practical example of how a data type changes the meaning of a bit pattern. Chapter 24. Why CPUs prefer 2's complement. 2's complement became dominant because it has several major advantages. There is only one zero. Positive and negative values can use the same basic binary addition circuitry. Subtraction can be turned into addition by adding the negative of the second operand. Sign extension is straightforward. And many arithmetic operations can share the same hardware. The result is simpler and more efficient digital logic. That is why 2's complement is so well suited to processor arithmetic. Chapter 25. 2's complement in modern CPUs. Modern CPU architectures use 2's complement for signed integer arithmetic. The same basic idea works for 8-bit, 16-bit, 32-bit, and 64-bit integers. For example, a 32-bit signed integer ranges from -2,147,483,648 to +2,147,483,647. The same 32 bits, interpreted as unsigned, range from 0 to 4,294,967,295. The hardware bits do not change. Their interpretation changes. Chapter 26. A quick 2's complement table. A 4-bit example makes the pattern easy to see. From 0000 through 0111, signed and unsigned interpretations are the same, 0 through 7. Then the signed interpretation changes. 1000 is unsigned 8, but signed -8. 1001 is unsigned 9, but signed -7. The pattern continues until 1111, which is unsigned 15 but signed -1. The important idea is simple: the binary patterns stay the same. Only their interpretation changes. Chapter 27. The key rules to remember. For an n-bit 2's complement integer, remember 4 rules. First, the sign ranges from -2 to the power of n-1 through +2 to the power of n-1 -1. Second, to create a negative value, invert all bits and add 1. Third, to recover the positive magnitude of a negative value, invert all bits and add 1 again. Fourth, another way to read a negative pattern is to treat it as unsigned and subtract 2 to the power of n. And when widening a signed value, use sign extension by copying the sign bit. Conclusion. 2's complement is the standard way modern computers represent signed integers. Positive values use ordinary binary representation. Negative values can be created by inverting all bits and then adding 1. For example, +5 is 00000101. Invert the bits 11111010. Add 1, 11111011. That is -5. 2's complement gives us only one zero and lets the same binary adder handle both positive and negative arithmetic. An 8-bit signed integer ranges from -128 to +127, while the same 8 bits interpreted as unsigned range from 0 to 255. The most important idea is this: bits do not inherently know whether they are signed or unsigned. Their meaning depends on how hardware and software interpret them. Understanding 2's complement makes CPU arithmetic, integer data types, overflow, sign extension, assembly language, and the ALU much easier to understand. This is Gate and Kernel. If you want to understand how computers really work, from logic gates to processors and operating systems, follow the channel for the next lesson.